ऑनलाईन, सर्व ऑनलाईन, जशीही झाली तशी.
याला सोडून. चालू.
नाही नाही, आता जोपर्यंत तुम्ही कॉलेजमध्ये येत नाही तोपर्यंत ऑनलाईन. ज्या दिवशी कॉलेजला आले त्या दिवशी ऑफलाईन असं. कॉलेज तुमच्यासाठी स्टार्ट केव्हा होणार ते आता आम्हालाही माहिती. मुख्यमंत्री सांगतील तेव्हा सुरू होणार. ठीक आहे. वचन द्यायचे.
Hello, sir. Can we start?
Yeah, we can.
Yeah, sir. In this labs, dear all participants, and today, good afternoon, everyone. Today is the third day of phase 1 AICTE sponsored online short-term training program on digitally controlled power converter for industrial and renewable applications under AQS scheme. Now, in the afternoon session, we are conducting the lab sessions from the INFOTECH Surat. Mr. Junaid Saeed is starting the lab session. So over to Mr. Junaid Saeed, sir. Sir, please start the session.
Okay, thank you, sir. Thank you so
Thank
much
you.
for
Yes.
introduction. So, first let us, am I audible to everyone, right? Properly?
Yes, sir.
Okay,
Yes,
thank you. So let us start today's sessions with the short revision of last two days. So first of all, I would like someone of you to say a quick summary of last 2 days, and that should be coming from the any person excluding the Yugal Kishore. Yes.
ऍक्च्युली काय झालं, ऍक्च्युली एचडी प्रोसेसिंग, एचडी विजन, ये वीडियो एकदम एचडी आ रहा है मेरा ये.
Please, someone of you. It will be short. It has to. It doesn't mean that it has to be a long summary. But just a few seconds it will take to just highlight what we have done in this last day and the before tomorrow, the day before yesterday.
Yes, sir.
Yes, Pawar sir. Yes.
Yesterday we have discussed how to program, and we have discussed the GPIO timer and DAC, digital to analog converter. We have discussed, and how to use the Visum software, the installation of Visum, how the MATLAB tool is used for this, Okay, and
Okay,
we have
yeah,
also seen the controller STM utility
yeah, yeah, yeah,
and the power circuit we also discussed, and we also seen some practicals. We have shown the videos of the practicals.
yeah, yeah, yes, yes.
Yes, sir.
So, yeah, thank you so much, sir. Uh,
Yes.
yes, switch interfacing. Sonia madam is saying, that, thank you, ma'am, thank you. So with that, we will move towards our today's topic. So today we are going to discuss first timers. We are going to discuss some about timers of the available in this STM controller. The basic timers, and advanced timers. And then we'll also see how to interface with the ADC and DAC. Okay, so that we are going to incorporate in this session. Okay, so with that, I will start my session. So I'll share my screen. Hold on a minute. Okay. Wait a minute. Okay. Okay. Now we can start. My screen is visible right now. Am I audible, everyone? And is my screen visible to everyone?
Yes, sir, visible, sir.
Okay, okay. Thank you, Yugal. So our first exercise, we will directly see the timer application through our this exercise. Okay, thank you. So our first exercise for today is basic PWM. So you must have done some high frequency pulses, generated high frequency pulses using 8051 and other microcontroller and Arduino. So you know that there are some lines you have to write in order to generate 1 kilohertz or 10 kilohertz or 50 kilohertz pulses. Okay, so in this exercise we will see that how easy it is to generate the high frequency pulses using this basic this Weijung environment in the MATLAB. Okay, so starting our first exercise, basic PWM. Okay, so before start there are two things I would like to ask in this is where we will get this uh, basic timer block. Please someone guide me towards how can I get this basic timer block.
It is available on the Vyjum block set, and the Vyjum block set we have the on-chip peripherals.
Okay. Yeah, it is right. Vyjum block set on chip peripherals, but which on chip peripherals? I'm not getting any.
STM32 F4 target.
Yeah. Okay. Thank you. And then we will see this timer section here. There you can get this basic PWM block. Okay. This is the location where you can get this time basic PWM block. And what are the changes to be, and also one more question about configuring this target setup block. So what will be the changes we will be making in this target setup block? Someone? Am I connected? Oh,
You are connected, sir.
okay, thank you.
We have to change.
Sorry?
Some changes are required, na? TS.
Yeah, but which changes are required in this in order to program our specific disk controller? What are the changes we have discussed yesterday?
We have discussed that base TS second, that is a point not one.
Yeah. But in this target setup block specifically, I'm asking.
Okay.
So these three changes is compiler, which is you have to select, then MCU you have to select which controller you are using, and the small changes, this STM program debugger you have to select, ST-Link utility which we have installed. Okay, so these three changes are there, just that you have to select. So then moving on to this basic PWM block, where we have get this STM Vyjum block set, STM32F4 target on chip peripherals, and then to timers we get this basic PWM block. And the few major changes are to be done is, it is so simple that you just only have to select the pins and the timer, which timer you have to you want to get this high frequency pulse, and you have to select the pins. Okay, so you can see which timer we have selected. So this timer we have selected is timer 4. Okay, and you can see the PWM period is 0.0001, which is 10 kilohertz, right?
So how many timers are there in STM32?
There are 17 timers available on the STM32. Okay, but okay, and we are there are some dedicated timers for specific program we can use. So there's only few this many timers you can use. Out of 417, you can use 14 timers. Okay. So this timer we have selected 4, which I will show you why we have selected this timer 4, and also this PWM period we have selected is what is the switching frequency here? It is 10 kilohertz. Okay. So let us first locate this timer 4 on our board. Okay. So I'm showing this board of ours. and please try to locate where is the timer 4 available in this board. And you see the pin numbers, which is D12, D13, 14 and 15. Okay, these are the pin numbers where we get this our high frequency pulse of 10 kilohertz. So try to locate timer 4 on this board. I'll give you just quick 2 minutes to locate it, 2 or 1 minute, whatever you. Please try to locate the timer 4 in here.
It's available in the GPO.
Yeah, exactly. It is available in the GPO. So here are the pins PD12, 13, 14, 15. So what is happening here is that the same pin are configured, we have configured for the GPO, the same pin we have configured for the timer. Okay. So you see this timer 4 here. If you select this timer 4, then you have the option of choosing the timer 4 at the channel 1, you have this pin available. Okay, if you are selecting timer 4 and at the channel 1 on from this 2 pin, on the whatever pin you select, you can get the pulse of this frequency pulse. Okay, am I getting clear, or is it confusing?
Please explain once again.
Okay, yeah. So let's say you have selected the timer 4, right? Okay, thank you, ma'am. So can I ask Mr. Yugal to keep your mic on? So
Okay.
okay, so this is timer 4 we have selected, right?
Mm-hmm.
Yeah. So and then some frequency we have selected 10 kilohertz. Okay, then
Okay.
we'll come to this polarity part later. Okay, don't worry about that. And then these are the channels available for on this timer. What the channel indicates is we can use this timer 4 and we can get the 4 pulses of same frequency, right?
That means if we select timer 5, then we will have the 5 channels.
No. Timer 5 it will also have the 4 channels.
Okay.
Okay.
Mm-hmm.
And these 4 channels have the dedicated pins, and if you want to get the under the channel 1, you can use the only these 2 pins.
Okay.
Okay, whatever you select, B6 or D12. Okay, so I say we have selected D12 here. On the channel 2 you have B7 and D13. On channel 3 you have B8 and D14. On the channel 4 we have B9 and D15 for the timer 4. Okay, so for the timer 4 you have total of 8 pins available. Out of that you can use 4 at the time.
Okay.
Okay, is it clear now?
Yes.
Okay, so let's say we have selected D12, so let's say select B6. So try to locate in this board where is PB6 or B6 pin.
It is available in the input GPI.
Yeah, GPI here, right? PB6. Okay, please explain again. Okay, so can you turn your mic on, Mr. Ma'am?
Yes, sir.
Okay, so which part didn't get?
This selection of timers.
Okay, so timer you can select according to your pin configuration. Okay, so let's say that was the only thing I was explaining, that we have selected this PB6 pin, right?
Yeah.
Right now, but PB6 pin is configured as a GPI pin in here.
Okay.
You can see it will only take the input for the controller. It won't generate the pulse.
Right.
Okay, but you have, let's say you have selected this PB6 pin and you are generating this 10 kilohertz pulse, it will generate the get 10 kilohertz pulse, but you won't be observing on this pin here. But if you locate PB6 pin on this controller here, this 100 pin controller, then on that PB6 pin you can get the 10 kilohertz pulse.
Okay.
Okay, is it clear?
Yeah.
Okay.
So
Hope this small.
we directly take the what we call the output from the PB6, then only we can get, right? B6.
No, PB6 you can directly from the controller if you get here. As I said yesterday that we have buffered this all of these 100 pins on this motherboard. Okay. So, but this pin, this specific pin, this PB6 and PC5, PC10, 11, 12, there we have only configured for the purpose of
Input.
general purpose input, right? That only function will be to give the input to the controller. They won't generate any pulses or give any signals out.
But if I am working with the board only, then we can use the
Yeah,
PB6.
if you are working with this board only, this small board, this daughter board or discovery board, you say. Okay, so on that pin you can get.
Okay. But
For the protection purpose, we have whatever we are designed here, the buffer ICs and protection we have provided. So that that are showing that this pin you can only use for the GPI function.
okay.
Okay, is it clear?
Yes.
Okay. So this channel selection is clear. This period which is our switching frequency, it is also clear. So let's come to this polarity. Okay. So in the polarity, we have this active high and active low. Okay. So let me close this and I'll close this one too. So I'll draw some figures and I'll try to explain it. Okay. So let's say this is our again, don't mind my drawing or handwriting. I'm drawing via mouse. Okay. So this is our carrier frequency, carrier wave. Okay. Let's say this in which range we've changed our duty. It is from 0 to 0 to 1, right?
Yes.
Okay, so our this triangle should be of 0 to 1 magnitude. Okay. Yeah, but in this case, this Weijung block set, they are creating this triangle wave in the range of 0 to 100. Okay, so the peak magnitude of this is 100. Okay, and this is 0. So if we want to give the duty, we give the duty of 0.5%, 0.5%, then we have to give it as a 50% duty. Then it will give some pulse here. Okay, reference it will take as reference here 50. Is it clear?
Yes.
Okay. So let us say we are I will take the first case for this 20% case. Okay. So let's say our we want to generate the pulse of 20% duty cycle. Okay, so this is some 20% duty cycle. Okay. I'm just writing high instead of active high. Okay, active high case, and with yellow I will show the active low case. Okay, so in the active high case, what will happen is the reference, which is this reference wave, and this is carrier. So it will give the pulse when the reference is greater than carrier. Okay, so reference is greater than carrier. Okay, and in this let's see first the, so here your reference is greater than carrier. Okay, so it will give the pulse from here. Okay, it will generate pulse here, and it is 20%. It will off. Okay, here, and again it is off, greater than carrier. Okay, again it is greater than carrier, and it will give pulse like this. So this is clear, right? Active low, high pulse. And in the active low, what happen will be that when in that case your reference will be less than the carrier. At that time it will give pulse. So your reference is less than the carrier here. Your reference is this, and your carrier is this. So it will give the pulse right here. Okay. At the same 20% duty cycle, if you keep the reference that active low pulse, it will give the pulse of 80% duty cycle. I hope this is clear.
And if you select 40%, that means 60% it will give high.
Yeah, exactly.
Okay.
In this active low mode, and if you select active high, it will give the 40%.
Is there any way when we use high and when we use low?
Can you explain it a bit more so that
how suppose I'm using one power electronics circuit in which I have to generate the pulse. So when it is recommended to use high and when it is recommended to use low?
Yeah, so let's say you are generating some creating some boost converter, like, okay. So in the boost converter, what happens is if you keep your switch on, the short circuit current will flow through the inductor and the switch. Okay. So in that case, if you keep it as a active high, so it will be continuously on. So in that case, you will have to use your in order to not do not turn that your MOSFET or IGBT on, so that you have to select as a active low pulses.
Okay.
Okay. So I hope this is clear. Okay. So this. So we are generating 4 pulses of this 10 kilohertz, and with the pulse of 20% duty, 40% and 70%. Okay. So we will quickly see the video of this experiment. Okay. If it is not audible, please inform me. Okay.
Okay.
Welcome to the demonstration of basic PWM time
Audible?
Audible, sir.
Okay, thank you.
operation of STM32 controller, and here this is the program for it using YZoom block set. So as we have already discussed that we are going to use a 4 channel. So all 4 channels are given with a different duty cycle. So we can give duty cycle between 0 to 100. And as we have discussed that inside this block some triangular generation is there. So that triangular will compare with this reference wave. This is, and it will generate a corresponding PWM pulse at PD12, PD13, PD14 and PD15 pins. And the period or the switching frequency we are setting in this block. So here we are giving a PWM time period. So that we have kept 0.0001, that is corresponding to 10 kilohertz. So we will see experiment. Suppose. So now here we can see that whatever pin of that timer, that is PD12, 13, 14, 15, it is terminated here with the buffer output. So here we are able to observe that PD12 is here, 13 is here, 14 is here and 15 is here. So now using oscilloscope, digital oscilloscope, one by one the PWM pulse generated we will observe from PD12, 13, 14 and 15 one by one. So for that let me connect a scope, first channel of the scope at PD12, second channel of the scope at PD13. So now these two we can observe from first channel and second channel. So PD12 we can observe at first channel and PD13 output we can observe at the second channel. So now we will go for the start. So in the oscilloscope the first channel output is taken from the PD12 and that we have set the 20% duty cycle, and the second channel is PD13 that we have set the 30% duty cycle, and switching frequency of this that we have set 10 kilohertz. So for measurement it we have already taken in the measurement. So we can see that the first signal switching frequency is 10 kilohertz. It's very stable and 10 kilohertz output we are getting. So this is the switching frequency of first signal and it is same as a second signal. Now duty cycle of first signal, that is this yellow signal, is 20%. So it is measured as a 20%. And the duty cycle of third signal is the second channel is 30%, that is set from at PD30. Now we'll change the output of oscilloscope channel at PD14 and PD15. So now it is PD14 output is here, PD15 output at here. So here also we are able to observe that the 10 kilohertz frequency is there according to our program, and duty cycle of the signal at channel 1, that is coming from PD14, it is 40%, exactly as we have programmed. And the duty cycle at signal at PD15, which is coming at second channel, is 70%. It is according to our code, and we can observe that frequency is 10 kilohertz. So now we will check this for the higher switching frequency. So let's check for some 100 kilohertz PWM operation. So we are setting timing according to 100 kilohertz. We will apply it and we will download the code. So when we press here, it will download the code. So wait for a while, it will be downloaded, and then we will see the output on the oscilloscope. So now it is downloaded. Now we will go for oscilloscope, and here, so PD13 and PD14 output we have connected, and here the frequency measurement is there. So here we are able to see that now the switching frequency is changed to 100 kilohertz, but the duty cycle is preserved like 40%, and the at PD15 70%. So PD15 and PD14 pulse we are taking out according to our code. Just the switching frequency change is happen, that change from 10 kilohertz to high value, that is 100 kilohertz, and the duty cycle is same 40% and 70%. So I hope you are very much clear with the operation of PWM operation using basic timer and its program. Thank you.
So I think it was clear.
Yeah, it is clear.
Okay, thank you. So let's move on to our second exercise of today, which is
Sir, can you explain the value which we have taken, the 20, 40, and like these are the constant value, na? Constant blocks of the MATLAB.
yeah, exactly, constant block.
Okay, sir.
So see, is there any major change you see in this block? Advanced PWM. Oh,
Sir, it is same as basic PWM, right? Yeah, it is different.
yeah, it is a bit different, but the major changes we will see in this block. Okay.
Okay.
So this block is same again. I am not repeating it. So see changes and that's all. And this is the major block we are talking right now. Advanced PWM. So you all are aware about that we want to generate, we want to develop our three-phase inverter. We want to give the complement pulses to the one leg switch, two switches of the one leg. Okay, as our same switch, the switches of the same leg should not be operated in the same time at any given time. Okay, so that to prevent the shoot through protection, shoot through fault. Okay. So that's why this block, which in the basic PWM block, it was just giving us one pulse of 20% duty when we are giving this 20% duty. But in this case, the advanced PWM block, it will give us two pulses. One of the 20% duty cycle pulse at the A8 pin, and the complement of this 20% duty cycle pulse, which will be of 80% duty cycle at the bit 13 pin. Okay.
Okay.
So that's the advantage of this block, and we will see the configuration, how we can configure this block.
You mean to say, sir, that means A8 can be used for A8 and B13 can be used for the one leg, and E11 and B14 are used for the second leg, and A8, A10 and B15 are used for the third leg.
Yeah, exactly. We can use it, but right now we are giving it this constant duty. Okay, we have to give the sine pulse in order to get the sine SPWM or any given control.
Yes, sir.
Okay, so this will be just our comparator will be the reference value will be our this constant value of 20%, 20. But in the SPWM mode, what will happen is our reference will be of changing. Okay, sine modulation, sine wave of 50 hertz.
Okay.
Okay. So in this advanced PWM, for the advanced PWM block, configuring this advanced PWM, we have only two timers limited to it. If you want to use this advanced timer, so you can use this out of these two timers, the timer 1 and timer 8. Okay, you must have noticed on this our board that this is our timer 1. Okay, you can see this is timer 1 and timer 8. It is written also advanced PWM. You can see PA8, PB13, P11, PB14, and PB15 pins. And same wise P6, PA7, PC7, PB0, and PC8, PB1 pin on the timer 8. So this is the pin configuration, how pins are configured on our board. Okay, so out of this timer, you have to select the which timer you want to use, and then this is PWM period, which is obviously our switching frequency, at which switching frequency we want our pulses to be. Okay, operate. Okay, so this is counter mode. So the counter mode we have selected is up, and this is counter mode down. So, and this is counter mode center aligned. So let us see. So the counter mode up means your pulses, your triangle will be your carrier wave will be like counter mode up. So it will be like this, and in the counter mode down, it will be like this. Okay, is it clear? And in the center align mode, it will be like this. Okay. Am I required to draw it properly, or is it
No, sir, it is
clear?
clear, sir.
Okay. So let me clear one more thing in this rough diagram of mine. So this is a counter mode up, and this is counter mode down. Okay. So in this case, if you are selecting this 10 kilohertz frequency, right? Okay. The 10 kilohertz pulse. So your this will be of your 10 kilohertz means 100 microsecond period. Okay. And again in this counter mode down, if you select this 10 kilohertz, your 100 microsecond will be like this. Okay, this will be the period 100 microsecond. And but in the case of this center aligned mode, if you are giving the 100 kilohertz, it means you are giving it the time period of this half. Okay. This will be your 100 microsecond. So your frequency will be half of this. Whatever you give, it will be the half of the whatever the value you select. So accordingly, you have to give the frequency in the center line or counter mode up or counter down mode. Is it clear?
Yes. So we have to select double.
Double, yes. You have to select double in order to get your required frequency. Okay. So moving on to the other things. Okay. So this timer mode is clear. This is a use date time selection. Okay. When I select this use date time, it is giving me this date time in seconds. So here we have given this 1 microsecond. So the 1 microsecond date time will be between this PA8 and PB13 pin. Okay. All of you are aware about why this date time is required. Okay. Date time in the first leg pin. This is your upper leg pulses, and this is your lower leg pulse. Okay. So this here will be the dead time. Okay. So this before turning on this lower switch, let's say this is S1 and this is S4 as our 1, 3, 5 and 4, 6, 2 configuration. Okay. So this is 1 and 4. Okay. So this is S1 and this is S4. So after turning off this first switch, this S4 will take 1 microsecond time to turn on. Okay. So that software deadband we can also provide using this. Okay. If you don't want to provide, you can also neglect this. Is it clear?
And sir, what is the standard value of that time? It will depend upon the model.
Yeah, it will depend upon your device.
Okay.
How fast your device is able to turn off. Okay.
So it will depend upon the what we call like data sheet and all.
IGBT, yeah, IGBT data sheet or MOSFET data sheet.
Okay.
Okay. So moving on to the things. So this is the break option. This break option we will see after discussing this point. Okay.
So
This was
I have one question, sir, like regarding this timer block. This is the
yeah.
timer block that is we have used in the last in the basic PWM. Same block
No,
we
no,
use.
no, no. This is not the same block. This is advanced PWM block.
Okay, that is
Sorry,
available
I
in.
didn't. Yeah, that same location. Sorry, I didn't show you that location again. I'm
Okay,
really sorry for that. The same location, but the block is different. This is at the advanced PWM. You can see
okay,
it was the previously it was basic PWM.
yes, sir.
Okay. You can see this property only in the advanced PWM block, not in the basic PWM block. Basic PWM block is simple. You have to just select timer, polarity, and just select the channels.
Okay.
Okay. So
So basic PWM, like we can the basic PWM can be used for the DC-DC converter.
yeah. You can use for the basic DC-DC converter.
Okay. Sir, if possible, please explain the both the operation. Like we have seen the input part and we have seen the output part. So can we combine both? Like we can take any input from the GPI pin and accordingly GPO will react.
That we can incorporate like right now. We will see if we can plan that in according to set it on our plan.
Yes, sir.
If it is possible, I will try it. Okay.
Because that part is very much useful for us, sir. Because
Yeah. I get that you want to generate some pulse and that you want to give it to the controller, right?
yes, sir.
Okay. We will see if it is possible. Okay. I'll check.
Yes, sir.
Okay. Thank you. So this is a output state. This will come to the later. And then this is first. Let us understand this output state. The output state it has three options. So output state enable means this it will generate this 20-degree pulse, 20 degree pulse on this A8 pin only. B13 it will leave it, and you can also use that B13 pin as a GPO port. Okay. Is it clear, Yugal?
Yes, sir.
Okay, and if you want to use only the B13 pin, you have to select this output and state enable. Just output and state enable. Okay, and output and if you want to use both of them, then you can use this output and state enable. So this is clear, okay?
So last one is not clear, sir. Last point
Last point is the same in this case, which we want to use the both of the pulses. Let's say I'm just giving 20% duty cycle, and now at the 8 pin I
okay,
want
right.
20%, and
Okay,
B13 I want 80 pulse.
to
So
use
that
both the pin, we have to select this one.
yeah. You just want to use the one pin, you have to select according to the whatever state you want to use. If you select output and state enable and give it a 20% duty cycle, then at the output of out on this B13 pin, you will get the pulse of 20%. Then and it will also be decided through this. Okay, the polarity high and polarity set when idle. Okay, so let's come to this. In this channel 1, and this is all just the channel 1 and 1N. 1 means channel 1 is indicating this A8 pin and 1N is indicating this B13 pin. Accordingly, this 2E11, 2N, B14, 3E10, 3N, this B15. Okay, so let's check these polarities. So in the polarity high and set when idle. Okay, so high and set when idle means, so let's say your timer is on, but it is not getting any duty cycles. the reference value. So at that time, what will be the state of it? Okay. So if you are setting this active polarity high and set, so it will be set as a the set means your 0 is reset and 1 is your set. So initially it will be in the high and set state, high and set. Okay. So whenever the controller is reset and your timer is not turned on, so in that case your timer will, this A8 pin will give you this one, the constant pulse of 5 volt or whatever the magnitude of your controller pin is. Okay. And if it is reset, high and reset, okay, then it will be on the 0 state. So this set reset is clear?
So no, sir.
Okay, let me try again. So let's say you are having this high set and high reset mode. Okay. So in the high reset mode, your timer is on, but it is not getting any pulses of the reference value of this is, let's say, uses your carrier wave, and this is your reference. Okay. So it is right now it is not getting this 20% duty cycle. Okay. So what will be the state of it? So at that time, if you select this set, so it will give this 1. Okay. So if you check at the proper particular pin, it will be giving you the constant pulse of one magnitude, 1 volt or 5 volt, whatever is the controller, according to the controller. Okay.
Okay.
And if you have selected this 0, the pulse will be of the 0. The pulse won't be there. Okay, it will be 0 constantly.
Okay, sir.
Okay. And the same way, if you're high and set, okay. So if you're high and set, then at the high, it will give the same, according to the same way in the basic PWM. If you have selected this 20, it will give the pulse of 20%. And if you are getting giving it a low, then it will give this of the pulse of 80%. Okay.
Yes, sir.
So I think these four are clear.
Yes, sir.
4 properties. Okay. So let's see the exercise. Video of that.
Welcome everyone for the demonstration of advanced timer program and its working. So here, as we programmed already, we have made program this. So in that first we will see that 8 signal at 8, which should be the 20% duty cycle. Pulse at E11, that should be the 60% duty cycle, and pulse at 810 pin, that should be 90% duty cycle. So first we will observe this 3 pulse, and that pulse should be of a frequency of 10 kilohertz, which we have set here. So now after that we will observe the pulse A8 and B13 simultaneously. So we can observe that B13 should have a duty cycle of 80%, and it should be exactly not of this. But if we have programmed, we have given some dead band, So that also we will observe in that demonstration only, that when A8 is turning off, after 1 microsecond only B13 will turn on. So there will be some 1 microsecond dead band. So that we will see. After that, here we have observed the B12 pin, that is for a break operation. So when we will connect a zero pulse, is active low. So when we connect the ground at B12, at that time pulse generated from these pins will go to the its idle condition. Idle condition means this. So here we have set all pulse idle condition is reset. So all pulse will go to the zero when we connect a ground pin to B12. So now in this kit, as we have discussed earlier, that the pin related to timer 1 which we have programmed already is terminated here. Pin related timer 8 is terminated here. So here we can see that our first channel output is coming at PA8 and PB13. These two are here, first and second. Then channel 2 is connected with PE11 and PB14, which is here. Then some ground pin is there. After the ground pin, here PA10 pin is there and PB15 pin is there. That is connected with channel 3 of advanced timer. So these are the 6 pin where we will get the output. So let me connect first PA8, that is a 20% duty cycle. Then let me connect PE11, that is a second channel output, that is 60% duty cycle. That should be 60% duty cycle. And third channel 3 output, that should be the 90% duty cycle. That 3 I have connected here. So channel 1, channel 2 and channel 3. So here first output will get at oscilloscope channel 1, second at oscilloscope channel 2 and third at oscilloscope channel 3. So now we will go for oscilloscope and we will observe the output. So now here in the oscilloscope, channel 1 is here, channel 2 is here, channel 3 is here. So channel 1 is coming from the timer pin PA8, channel 2 is coming from timer pin E11 and channel 3 is coming from A10 pin. So here we are observing that this pulse is of duty cycle 20%, which is here. And all 3 signal are with a frequency of 10 kHz that we have programmed. And second channel, which is coming from E11 pin, its duty cycle is 60%, that is visible here. And third channel, its duty cycle is 90%. This is according to our code. So this is all about the output of channel 1, channel 2 and channel 3. Now we will see the A8 output, that is a channel 1 output, and the other pin output is at B13. This is the CH1N channel, means not of this signal we will observe here. Now we are removing these 2 pulse, channel 2 and channel 3. Now we will observe the pulse from channel 1 pulse and its 1N pulse, means it's not pulse. These 2 pulse. So first is first channel of DSO, second is the fourth channel of DSO. So now we will go for digital oscilloscope. So here we can observe that the first pulse is with 20% duty cycle and fourth that we will take inside the measurement. So source 4 duty cycle, that is a reverse of that is 80% duty cycle. Now this pulse is not pulse of first channel. So this is the we give to the inverter H1 higher IGBT, and this is to the lower IGBT or lower switch of one leg of inverter. But here some dead band also we have programmed, that we will see here. So see, so when the second switch is turning off, after some time only the upper switch is turning on. So here we are able to see that during this time both switch, upper switch and lower switch of same leg will be off, and that is of 1 microsecond. Here 1 microsecond is there, that is a time per division. So per division 1 microsecond there, So this dead band is 1 microsecond. That is according to our program. So we are having here programmable dead band. So we are having the 3 channel and all channels are giving its not pulse. So similar to this. So we have now observed the output at A8, E11, A10 as well as the relation between A8 output and B13 output. So output at B13 was a note of A8 as well as between these two this deadband of 1 microsecond was there, and the frequency of signal was 10 kilohertz, that is according to our code. So these two things we have seen. Now we will see the other aspects. So here I have already discussed that the break operation we can do using B12. So here setting was that so enable with input active. So when we give this low pulse means ground pulse at ground or zero magnitude voltage at B12, when we connect the ground of a circuit at B12, at that time all the pulses output coming from this, immediately it will turn off. Immediately it will turn off and it will go to the idle condition. So what is idle condition? Now ideal condition means this. So here it is written that we have said that so when idle condition is there, at that time pin should be reset. So we have said that all the output, all 6 output 1, 2, 3, 4, 5, 6 all become 0 when we connect a ground with B12. So that we will see in experimentation. Now so here we are observing that all pulses are coming. Now we are going to see the break operation. So to make it break or to turn off this pulse, what we will do is here in the controller circuit ground is there here. So I have connected this connector at a ground. From ground I will connect it to the PB12 pin which is here. So when I put it in PB12, at that time you can observe in the oscilloscope that it will stop immediately the pulses, and that pulse will again start after clearance of fault or after reset of the controller. So now we will see that when I connect it, you can observe, please observe in the oscilloscope. So now you observe in the oscilloscope, when I connect PB12 with the ground, the pulse will stop. You can see pulse is stopped. So if I remove again PB12, then also it remain off. Unless I am not resetting the controller, pulse will not off. So let's see in the scan mode. So in the scan mode, if we see, so that pulse will off when I press, when I connect to the PB12. See, immediately it stopped. So this was the programming of advanced timer and its output. Thank you.
Hope it was quite understandable. Okay. So shall we move on?
So the utility of this function for the protection, right?
Yeah. That utility was the for the protection purpose.
Okay.
Shall we move on to our next exercise?
Yes, sir.
Okay, thank you. So before we move on to our exercise, I would like to take a small break here. And is it okay, Paresh sir? Can you take a break?
So please provide your contact details so that we can we can have some connection.
Okay. Yeah, Paresh sir. Yes. I will
Hello?
take a small break here. Okay.
Yeah, no problem. You just take a break of 5 to 10 minutes and we
Okay.
request all the participants to stay in the meeting.
Okay. So we will continue at 3:45.
Okay, no problem.
Okay. Thank you.